Hello, and welcome to the lecture for Chapter 19 of Conceptual Physical Science, 6th edition. In this final chapter in the chemistry unit, we're going to talk about organic compounds, wrapping things up with the most complicated form of chemistry, organic chemistry, just because we know so much about it and it's so tied in with another field of study, biology. But that's not included in the physical sciences. We're not talking about biology here, but certainly we're getting close when we're talking about organic chemistry, which is the study of organic molecules or organic compounds. After this final chapter in chemistry, we're going to move on to geology, topics of earth science and weather science. So we're wrapping things up. Also, looking at this table of contents, I want to make it clear that in this chapter, we're not going to be covering many quantitative ideas. More than in any other chapter, we're just going to do a survey of some interesting really compounds, some common compounds. What do they look like? What are some trends? There's not too much that you're responsible from this material. And that's really a testament to the fact that it's so beyond the scope of the class to study organic chemistry in a meaningful way. So we're really just touching on it here. Okay, so let's see what we're going to look at. We're going to talk about hydrocarbons. So what does that mean? What does a hydrocarbon look like? We're definitely going to want to distinguish between saturated and unsaturated hydrocarbons, something you're going to be responsible for. The general definition of a functional group, but we're not going to get into it too much. We're going to look at examples of alcohols, phenols, and ethers. Okay. Also, we're going to look at examples of amines and alkaloids and carbonyl compounds. This is a really light part of the lecture. It makes up a lot of slides, but it's mostly just pictures of the molecules, and I'll be going through it rather quickly. And then finally, we're going to talk about polymers, just what's the definition of polymer, and some interesting things about how common they are in terms of man-made polymers, as well as organic polymers, or those that come from plants. Okay? So what is organic chemistry? Well, it's a branch of chemistry involving the study of carbon-containing chemical compounds, right? You might think, oh, tied in with life, but a good definition is carbon-containing because every molecule that's involved with living organisms from bacteria to whales includes carbon-containing compounds. Carbon is in all these organic molecules. Okay, so there's definitely something special about carbon, and I hope that's a good takeaway from this lecture. What is so special about carbon? That is, well, a carbon-containing chemical compound is an organic compound. It's two ways of saying the same thing. Got that? Okay. They're natural, but they're also synthetic, right? They can be made in the lab, and they can be made by plants and animals. Okay, there are 100,000 new ones discovered each year, either discovered within plants and animals that we had not analyzed completely up to this time. There's plenty of examples of that, and ones that are being mixed in labs. Okay, there are over 13, almost said 3 million. There's over 13 million known, and that number is obviously growing at a rapid rate. So you're not going to memorize all 13 million. Okay, so why is carbon so special though, right? Why is it in these 13 million known compounds? Well, because carbon has atoms that connect with one another through strong and stable covalent bonds. And I would recommend reviewing what covalent bonds are back in our lecture on chemical bonds, because it's important to have that definition. We'll see it a bit here in passing, but it'd be a good thing to review. Okay, so here are some examples of molecules, okay, both organic and otherwise. Here's an example of a bunch of carbon together, nitrogen, oxygen, and sulfur, okay? So you can have covalent bonds between all these different types of elements, okay? However, let's compare their bonding energy, their binding energy, because if you notice, the value for the covalent bonds, a single covalent bond here, between these two carbon is greater than any of the others, okay? So all these other cases where you could imagine multiple nitrogen, multiple oxygen, or multiple sulfur chaining together, their bonds just aren't as strong. That means that something like sulfur 8, like this, is very unlikely. It's very rare because it's just an inherently unstable chemical bond based on the energies, okay? Because there's this whole idea of, energy, entropy, least energetic processes most likely to occur. Well, that's the underlying story of carbon. Now, looking at sulfur, not as much binding energy, very unlikely for sulfur to build a molecule like this, okay? And that's a universal truth except for carbon, okay? Carbon is special. You can have carbon in incredibly large chains, incredibly large grids of bonds between multiple identical carbon atoms. For example, something like this is diamond, okay? One of the strongest substances out there. So, what also makes carbon special is it readily forms bonds with many other types of atoms. So not just stable covalent bonds between carbon, that's special on its own, but also its ability to bond with so many other atoms. Okay, it has those 4 valence electrons. There's just so many different configurations, almost an infinite number of them. Not all of them are useful necessarily or have known uses, but there is almost an infinite number of combinations. Okay, so to appreciate organic chemistry, please minimize the memorization. It's not about memorizing them. Obviously, you're not going to memorize 13 million different compounds. I don't want you to even memorize the compounds I show you. I just want us to get a passing look at them. Okay, so a hydrocarbon is a term I do want you to know, and it's a chemical compound containing only hydrogen and carbon. Okay, so nothing else, nothing else, no nitrogen, no oxygen molecules, nothing contaminating this pure hydrocarbon. Okay, here are examples of hydrocarbons. All right, so these molecules are relatively small, but they're larger than the smallest molecules that we've often been using as examples. Here we have pentane, we have isopentane, and we have neopentane. Lots of names for these. Okay, here is the molecular structure shown in a covalent bond way. Okay, this is the same form of showing molecules that we presented back in the chapter where we presented covalent bonds, right? One line represents one covalent bond, right? This is the same or very similar notation as using dots around the letters for the element to represent valence electrons. And if we were doing that, by the way, we would show the valence electrons around the carbon like so, right? So we'd actually show it like this, okay? This is the way we show the valence electrons around carbon, okay? But here we're instead showing the covalent bonds between carbons and between carbon and hydrogen. Okay, hopefully that makes sense. And again, it's something we've seen before. This below, this alternative notation, a very minimal notation, is another way to represent specifically hydrocarbon molecules. Only works for hydrocarbon molecules because it is so simplified. We'll talk about how to read those that form of molecular drawing in just a second. Okay, but this pentane has 5 carbons and 12 hydrogens. This one also has 5 carbons and 12, and so does this one. The only thing that differs is the shape, okay? And that is called the structure. These are structural isomers. Isomer refers to the fact that they actually are composed of the same atoms. Iso means same. So they're an isomer because they all have 5 carbon and 12 hydrogen, each of them, see? All right, so they are all isomers and they only differ in structure. Molecules having the same molecular formula, but different structures. However, we can take the word structure and make more sense of it calling it a configuration, because that's the way we see it, right? And that is probably a less technical term. So a configuration is the specific way in which the atoms of a molecule are connected to one another. Okay, so configuration just means connectivity. So whether you call it structural form or its configurations, connectivity, we all mean the same thing, just how they are actually oriented in space. Okay, all right, and we certainly saw it here, right? It's just they're just situated differently. Okay, they're just chained together differently. Okay, so here are examples of chemical formulas of particular numbers of carbon and hydrogen, so particular hydrocarbons in their chemical equation form, and the number of possible isomers determined by scientists and mathematicians based on how you can arrange them differently and still have them be a unique molecule. So there's only 3 possible orientations for this relatively small chemical molecule, or just molecule. But as we get into larger molecules with more carbons and therefore more hydrogens, the number of possible isomers grows dramatically, all right? Right, so as we get up to very large combinations, there are hundreds of thousands of possible isomers. All right, okay, so quite interesting there. Now, a conformation is the name of the different spatial orientations of a single configuration. It's a bit confusing the similarity between these terms, conformation, configuration. It just means we've changed it, right? It's a new conformation of that hydrocarbon. So for example, if we rotate this bond, right, now we have a pivot, like pivoting an elbow, and this is a new conformation of this configuration, all right? So these are 2 conformations of the same configuration, All right. So within a configuration, we can have conformations. Because we saw before with the different configurations, they were literally bonded differently, right? The carbons were situated relative to the other carbons and the hydrogens in different ways. Not so here. The only difference is a bend. It is simply a swivel without any actual swapping of locations between carbons and hydrogens. And if you want to really kind of drive that point home, I think it's important to go back and show that in these cases, right, we actually saw different ways that they were oriented relative to each other, right? Because here, for example, a carbon is connected to 3 carbons and a hydrogen. Here, a carbon is connected to 4 carbons. So it's actual different configurations despite having the same sum number of carbons and hydrogens. Not so for conformations. Everything's the same except that twist, okay? But even that matters. So you could certainly imagine that within a certain configuration, there are numerous conformations, which adds significantly to the number of isomers, okay? If you include conformations. So now let's read this type of drawing for a molecule, for a very specific molecule, a hydrocarbon, a molecule with only carbon and hydrogen. So what is the chemical formula for this structure, okay, in this particular conformation, okay? All right, well, what is it? How do we read it? Well, the way we read it is each endpoint of the line is a carbon. So 1, 2, and I know I showed you the answer, but 1, 2, 3, because they didn't expect us to know how to do it yet. 4, 5, and if you did, that's great, by the way. So each of those must be, each endpoint of a line, which includes the joints between lines, must be a carbon. So every one of these is a carbon. So we simply count 5 that way, okay? Then we look at all available slots for more bonds, and we put a hydrogen there, because we can't have an empty valence electrons, right? Because then we'd have an ion, and furthermore, I guess we wouldn't have an ion, but we'd have a molecule that would inherently want to bond with something else. It wouldn't be stable, okay? And so every spot, because remember, carbon can make four covalent bonds, we have to put a hydrogen. So we put a hydrogen, one over here too, in every available spot. Okay, so you can see how you start to fill those in. There'd be, only 2 here, right? Probably one there, hydrogen, hydrogen, see? Okay, and so on, all right? So here's the idea, drawing the C in, drawing the H's in, just like that. Okay, so now every carbon has 4 total bonds, okay? And then we do that, then we just count the number of hydrogen atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's how we know that it is this particular hydrocarbon with 5 carbon and 12 hydrogen. Okay, and by the way, hydrocarbons include fossil fuels. So as we get crude oil out of the ground full of hydrocarbons, we can then basically distill it, get the crude oil vapors with the heaviest down at the bottom, which is the tar, which is also the warmest region, and then lubricants, diesel, kerosene, gasoline, and natural gas in terms of lighter, cooler byproducts of the distillation of crude oil. Okay? All hydrocarbons. Now, an unsaturated hydrocarbon is a specific case where there are other, when there are other bonds between carbon that aren't single covalent bonds. Okay? What do I mean by that? Let's see. Okay, so what we're going to define here is an unsaturated hydrocarbon. At this point, we've only been talking about saturated hydrocarbons. I'll repeat the difference between the two in a minute, okay? But let's remember carbon always has 4 bonds. That's what allowed us to read that molecular diagram back on the check a minute ago, okay? So here are the bonds shown, all right? There's the 4 valence electrons, which allows for 4 bonds, making something like methane, and this is the way we draw it, right? Depicting the covalent bonds as lines. Good. Okay, or we can depict the covalent bonds like this. Okay, and that reminds me, when we draw carbon by itself, when it's not bonded, it is just 4 single dots. So please excuse me drawing the extra dots above. We'd only draw the extra dots if we were using this notation for covalent bonds, okay? Which is not necessary because we prefer just to draw the single line. It's easier, right? Or we could redraw this as just, in this case, it would actually be trivial. It would just, it wouldn't make sense to use the line notation here because there's just 1 carbon. So you can't have a line if there's 1 carbon. It's just the dot. See? So not good for the line notation, but good for using just the notation of valence electrons, or rather the notation of covalent bonds, right? Shown. Okay. So some of these bonds, however, may be within multiple bonds. So in other words, instead of having single covalent bonds, which is what's shown here, we can have multiple covalent bonds, which is a notation we presented and we've seen before way back when we first had our chapter on bonds, molecular bonds, okay? So then you can go from a saturated hydrocarbon, okay? Saturated because every bond matches to a different atom. Take this carbon, for example. It touches 4 different atoms. If that's the case of every single carbon, then you have a saturated hydrocarbon. But if some of the carbon are double bonded together, well, now you have atoms that only touch 3 other atoms. This carbon only touches 3, as does this one, okay, because of the double covalent bond. That means that it's no longer saturated. There aren't as many atoms as there possibly can be. Saturated means maximum number of atoms in the molecule. This one has 1 less, or rather 2 less, of the maximum number of atoms that could be in this molecule, okay? Because of that double bond. That makes it unsaturated, okay? And like we talked about, saturated fats, unsaturated fats, same idea here, but it's saturated and unsaturated hydrocarbons with different names, butane and 2-butene. All right, so unsaturated hydrocarbons are a hydrocarbon containing 1 or more multiple bonds. A special case of an unsaturated hydrocarbon is the benzene ring, which is pretty neat. So it's a case where you can have every other carbon, because that's what's going on here. Remember, each end of the line, which in all of these are junctions, so every other one is a double covalent bond. So this carbon has a double covalent bond shown here with its neighbor and a single covalent bond with its other neighbor. All right. How many bonds does that leave open? Just a single one. So there could just be 1 hydrogen on each of these, as depicted here in this more 3D version of it. Okay. And any orientation of this benzene ring is valid. You can rotate it, which is shown here. I just rotated a certain amount, and you get the same result. It's just that every other bond between carbons is a double covalent bond. And we have a funny, unique way of drawing it, where we represent those alternating covalent bonds as actually a circle. So this is actually alternate notation, where we show the double covalent bonds as a circle within, which denotes the benzene ring. The reason that scientists would do that and have this special notation is because the benzene ring is usually part of other larger molecules, like toluene or naphthalene or dichlorobenzene, okay? Notice that dichlorobenzene also contains chlorine, which we haven't seen yet, but certainly hydrocarbons aren't, you can have hydrocarbons and then you have mixtures of hydrocarbons with other atoms. Okay, well, let's do this again for reading the notation, this special notation of drawing carbon. So what is the chemical formula for this structure? Remember that there is one single case of a double covalent bond, right here. But now you've done it once, or I did it for you once. See if you can count the number of carbon and the number of hydrogen. And the number of carbon should be easy. Make sure you carefully count the number of hydrogen. Okay, do you have your answer? It's C5H10, right? So same number of carbons, 1, 2, 3, 4, 5, as we showed before, but we have 2 fewer hydrogens. Why is that? Well, because look, we can only have a single hydrogen in each of those carbons, as before they each could hold an additional hydrogen. So our final result looks like this, and we can clearly count 10 hydrogens and 5 carbons. Okay? So far we've only been talking about hydrocarbons. There are also heteroatoms, which is an atom other than a hydrogen or carbon in an organic molecule. So a hetero, meaning different, atom, all right, is any atom other than a hydrogen or carbon, right? And so it's the name of the thing you're putting in, like the chlorine we saw before. That would be the heteroatom. A functional group is a combination of carbon, hydrogen, and those heteroatoms that behave as a single unit. So again, part of larger molecules. Right? So organic molecules are classified by the functional groups they contain because it helps make sense of the huge number of different combinations, but there are usually these very important functional groups which allow for the actual human mind to study them, right? Because otherwise it's too much, only computers can understand this information. Okay, so for example, let's look at some functional groups. Here's a functional group ethane, ethanol, and ethylamine, okay? Notice that ethylamine and ethanol both have a heteroatom, whereas ethane is a pure hydrocarbon, okay? So in which of the following structures is carbon bonded 5 times, okay? So this is not talking about heteroatoms so much, although there are certainly some examples of them in here, like the oxygen shown. Instead, this is just making sure we can, again, read these types of notations, these types of diagrams for hydrocarbons, okay? Or just, in this case, hydrocarbons including heteroatoms, but still showing these covalent bonds this way, right? And not writing in, we write in the heteroatoms. Anytime a heteroatom is there, it's actually included in the picture, but the carbons are always implied, right? Which makes it easier to read, right? We're not writing in every carbon, even though they're there, okay? So which one of these has carbon bonded 5 times? Count them out. Okay, well, turns out it's a trick question. all right? Because carbon can never be bonded 5 times. It can be only bonded 4 times. That's the rule, right? That's the number of valence electrons it has. So it's a trick question that is impossible. Let's ask it a different way. In which of the following structures is carbon bonded 5 times? Okay? Well, didn't I just say it's impossible? Yeah, which means that one of these is actually a mistake. One of these is impossible. Which one is it? A, B, C, or D? Someone drew it incorrectly, let's say. It's C, because it does show 5 bonds, which is impossible. This is not a real molecule. It cannot exist based on the laws of physics and chemistry. Okay, so let's run through some example compounds, some example molecules. All right, so here we have the hydroxyl group. This is one of those functional groups. Okay, alcohols contain the hydroxyl group. This is what it looks like. All right, and we're using slightly different notation, clearly showing the carbon in this case, but still. All right, methanol is an example. All right, with a boiling point of 65 degrees Celsius. Ethanol is another example, right, that includes that same functional group, the hydroxyl group. So see how it shows up in each one? All right, has a higher boiling point. 2-propanol has a higher boiling point still. All right. There are also phenols, which all include the phenol group. Notice that the phenol group has a benzene ring. Okay, this is what the phenol looks like, the phenol group that is. All right, phenols are acidic, right? So they inherently are going to have that ability to give up a proton, right? So we have, that, or rather, bases accept, yeah, and then acids donate, right? So give up a proton. That's what phenols are doing since they're acidic. They give up a proton. So we'll just write a hydrogen plus a hydrogen ion. Okay, so here's just a picture of the phenol. Examples of molecules within the phenol group. We have 4N hexylresorcinol. Hopefully I got that right. Thymol. And then we have the ether group, another functional group, which has an oxygen squished between 2 carbons. Dimethyl ether includes it, or ether includes it, with a very low boiling point, so it's going to be in a gaseous phase at room temperature, even at 0 degrees Celsius. All right, there's ethanol with a much higher boiling point. All right, we have diethyl ether, okay, and then we have the amines and the alkaloids. So the amine group includes this nitrogen, all right. So ethylamine is an example. We also have the carbonyl compounds. So carbonyls are another functional group. This is what the functional group carbonyl looks like, an oxygen with a couple of carbons, okay? And ketone is included within the carbone group, or kind of closely related to it, as is the aldehyde group. There's also acetone, which is part of that group, and acetaldehyde, all right, as well as formaldehyde, all right? Citral, all right, this is included in citruses. It gives that citrus taste. Here's the molecule citral, right, part of that group. Cinnamonaldehyde, which is related to the cinnamon smell, no surprise there. Benzaldehyde, and vanillin, related to the smell of vanilla. The amide group is included in molecules like this one, which I will not try to pronounce, but is shortened as DET, or DEET, which is a somewhat older news, but from many decades ago, it was an infamous pesticide, all right, because it negatively affected things other than just small pests. We have the carboxyl group, the salicylic acid, and including acetylsalicylic acid, right, within that group, including that benzene ring right there. Okay, this is aspirin, by the way. All right, there's the molecule for it. The ester group, which includes salicylic acid and a chemical reaction to make methyl salicylatate, which is wintergreen. Right, that's that smell, that flavor. It triggers cells within our body, and it gets recognized as wintergreen. By the nerves in your tongue. We have penicillin, right, within that group. Now, finally, our last topic of the lecture: polymers. What is a polymer? Well, polymer is a very long organic molecule, okay, so very long, and it's a molecule, made by the joining together of smaller organic molecules, known as monomers. So it's a chain of identical pieces, like a chain, right? Each piece of the chain, each link of the chain is somewhat identical, same idea here, okay? So it's monomer, 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 one after the other, okay? So the chains, the monomers, can be things like ethylene, all right? So here's a couple of ethylenes next to each other, implying that we're going to chain them together. And when we chain them together, we can get what's called an addition polymer, where the mass is equal to the sum of the monomers you put into it. So you simply put in the monomers and they form a chain. Just everything is conserved, all right? Nothing is lost in the process. So here is that ethylene chain, right? This is our long chain of those monomers making a polymer, All right, this is polyethylene, okay? Propylene, right? Here's the monomer propylene. If you have a chain of propylene, then you get, you guessed it, polypropylene, right? These are famous plastics. Okay, you can have polyvinyl chloride, another example of an additive polymer. Okay, you can also have Teflon. All right, famous for its lubricating properties, and we know because of the fact that Teflon has such low electronegativity that it's not really interacting, it's not sticking anything. Okay. You can also have a condensation polymer. This is the other type other than the addition polymers or additive polymers. This is a polymer, excuse me, that's formed when the joining of the monomers is accompanied by a loss of some other molecule, such as H2O, getting basically created as a byproduct and not contained in the polymer chain. So here's an example of putting adipic acid with hexamethylendenamine. Hopefully I got that close. Combining them together, having a byproduct of water, all right, and then forming basically those two monomers together, so one chunk of a chain, and then doing that process over and over again with each then, two pieces of the chain that had the two building blocks coming together to form one long polymer known as nylon. Okay, but notice that water was produced as a byproduct of the creation of that polymer. All right, that's why we call this a condensation polymer. Okay, and natural products synthesize polymers as well. All right, so and one of the most common monomers that plants use is isoprene. Okay, so it makes plants and other organisms besides in the plant kingdom will make chains out of isoprene. We saw one of them already, which is citral. Right, that's a chain of isoprene. We can see two of them here. Right, so it's a rather short polymer, but there are longer examples, including beta carotene, which is clearly a chain of many of those isoprene. Okay, monomers. So is monomer a functional group? Not really, because of the way it's classified, but they're closely related because as you saw in both cases, whether we were talking about a functional group being part of a larger molecule or a monomer being part of a long polymer, it's all about finding these common building blocks. And again, I hope just some of these ideas rung home, or that you're interested in looking up some of these molecules and seeing about what they're used for in our everyday lives. Well, thank you so much for watching this lecture. I hope it has been interesting.